Hey everybody, welcome back to this course. In this video, we're just going to go over lab 4, week 4 material. So let's share this. So this week we're looking at noise, communication, and spectrum analysis. So here's some of the background. We're going over a high pass filter. If you recall last week, we went over a low pass filter. And then we're going to use our low pass filter and high pass filter to create bandpass filter. And so let's quickly just review some of that from last week. So last week we had a low pass filter whose topology looks like this. And so over here is where we apply some input voltage across these two nodes. And then over here is where we observe the output. And so we've got some R and C that result from resistance and some capacitance. And we found that there's a cutoff frequency at 1 divided by 2 pi times that resistance times that capacitance. And so it had some characteristics, right, that look like this. If we're looking at frequency, well, at this cutoff frequency, so at FC, we start to notice that the amplitude, right, so it's just some arbitrary amplitude. The amplitude of our signal starts to roll off around our cutoff frequency here. So this week, we are going to be looking at what happens when we have a high pass filter, right? So this is a high pass filter. We just switch the order of the resistor and the capacitor. Right, so here's R, here's C, and now here's where we input our voltage. Here's where we observe the output. Right, so I guess this A here is more like the amplitude of our V out. Right, so just call that like V out, biggest bars or something. So with this kind of topology, we have the same equation for cutoff frequency. But now instead of at this cutoff frequency, we start losing the signal after that. We're passing more signal after that, and it starts rolling off at these lower frequencies. Right, so it's a high pass because it passes through these higher frequencies. And so going back to that bucket of water analogy, right? So if I just apply, I just have a capacitor, right? As we apply this positive voltage, it fills up this bucket of water up to a point where it gets so full that it gets the amount of charge that it is seeing being applied, right? So it gets so full. And so then if we just look at something, right, so just say we're applying 5 volts directly to a capacitor. Well, at some point, this capacitor is going to fill up so much that there's going to be, actually, let's take a step back here. Let's look at what happens in our low pass filter case when we just apply 5 volts directly here. So at some point, the charge builds up so much in this capacitor, the energy just that's being stored builds up so much that it gets the same voltage that it sees being applied to it, right? So here at this node, over time, becomes 5 volts. And that's why once it fills up, it starts to roll off, right? So the voltage of our signal starts to roll off. In the case of a high pass filter, we've got applying our 5 volts. So now in this case, the node here, right? So the total drop across this capacitor is going to be 5 volts. And so sorry, this this might be a little more confusing, right? So the total drop across this capacitor is 5 volts for this low pass filter. Now in this case, the total drop is going to be 5 volts. And so this voltage at this resistor here is going to be ground, right? Because there's not going to be any more potential for current to flow, really. Which is why at higher frequencies, right? So we're emptying the bucket fast enough so that it's not filling up all the way. So that's just the idea of these two filters. But then when we cascade them together, right? So here we have a high pass filter, right? And then this is the output, right? So this is like the out one or something at this node. Then we pass it into the low pass filter. If we set it up correctly, we'll have a frequency characteristic that looks like this. Right, so we have, let's just say, right, so here's our, our high pass filter stage with the FC1. And over here is our low pass filter stage from FC2. Well, if we look at the frequency characteristics, if we have FC2 that's greater than FC1, then we have a curve, right? So past FC1, it starts to roll off because it's a low pass filter. And then past or below FC1 is where the signal starts to roll off as well. But in between here, right, it's passing through all of these values, which is the idea of this bandpass filter. So in lab today, we're going to construct a bandpass filter, and I would just use the fixed resistor. So maybe this is R1, this is R2, and so maybe use R1 equals R2, 100 ohms or so. And then you also have two capacitors. You have one capacitor, I think that's 10 microfarad, and you have another capacitor that's 100 microfarad, right? And so you want to figure out where to put these two capacitors to get some frequency characteristic that looks like that. Let me take a look here. So to analyze the voltage transfer, we're going to be using this SPICE tool. So specifically, we're going to be using LTspice. And I think I'll walk through that in a bit. Yeah, we can do that now. Let's see. I think I'm sharing. So this is what LTspice looks like. You open up, let's just walk through this. So you open up a new schematic, right? And you can press F2, get a new component. In this case, we'll just use a sign. Yeah. I'll just build up a low pass filter here for you guys. And then I think Control Command R on Mac will rotate this. Right, so we put the resistor and we get a capacitor. And then we can click W, not W, function F3 to connect these all together. And then, so we need a ground, so we do function F4. Get ground. You can connect it here. Now we can set this resistor to 100 ohms or so. Set this capacitor 10 micro, so you can just do a U for micro. And we need a spice directive, so we need to know how long to run this. So this is going to be transient, so we're looking at the time analysis. We're going to run it from 0 to 5 milliseconds, and we're going to have a sampling of 1 microsecond. Hit OK. Now we hit this little running man, and it'll bring up a oscilloscope basically. And so looking at this, right, if we click back on our schematic, if you click on a node, it'll plot the voltage at that node. If you click on a component, it'll plot the current going through that component. Right, so we want the input, which is here, right, because we've already told the system where ground is, right? So we just click that. Yeah, now it plots the voltage at that input node. And then you click on this, and here's our output. Right, so 110 micros, so our cutoff is 1 divided by 2 times pi times 100 times 10 to the minus 6. Right, so our cutoff is 150 hertz, but our sine wave, right, is 1,000 hertz. Right, so this is going from 0 to 1. That just means that our amplitude is 1 volt, so we can change that to 5. And here we can change the frequency to something that's on our passband, so maybe 100 hertz. And then if we run that, it will show that new plot. And then here, right, you can just, there's we don't really need a measurement tool, right? We can just hover over where we think the max is. So our max input is about 5 volts. And then our output is about 4.2 volts. And then going back to this, let's pause. Right, so our transfer, we call that H usually. So our transfer at a frequency of 100 hertz is equal to 5 divided by 4.8. Sorry, 4.8 divided by 5. Right, so this is kind of just a measurement of the efficiency. And you can see that that's about the transfer at 100 hertz is about 96%. Let's take a look back here. So that we went over how to use LTspice. We talked about the theory for all these filters actually. Simulink, we'll go over that. Let's see what is in this. So far we've done this. During lab, we're also going to build our bandpass filter, right, using the components from our kit. And then for part 3, we're using filtering techniques to improve the fidelity of an audio recording. Right, so we'll go back to my desktop here. I think it's sharing. So here on the desktop, right, so when you have MATLAB opened up, you'll need to install Simulink with this add-on button again. Here. So we pull up Simulink, and I have this model set up. So I think to use some of these blocks, you're going to also need the audio toolbox and the digital signal processing, so DSP toolbox installed. So when you're getting add-on, also get those too. And I think it mentions it in the lab manual. So that should be fine. Right, so here's just an example Simulink model that I've created here. Right, so it uses this from multimedia file block, and I uploaded this multimedia file, so it's just an audio recording. And then the idea, right, so you're not going to have this initially. We're going to comment that through. But when we run this, it'll plot the audio spectrum of that signal. And you're going to want to look at the frequency band and determine, first of all, what kind of filter you want to use, which I guess is kind of obvious here. What kind of filter you want to use, and then if you double click that filter block, you should be able to change the pass band frequency, right? And then the stop band is where it's like mostly completely cut off almost. And don't worry about these, but just determine where is a good range of attenuation. And then you're going to use this buffer block just like make processing a little bit faster. And then the spectrum analyzer block and this audio device writer. So right, to get a block, suppose we want to just look for a high pass filter or something, you just double click the white space and look it up. It's a high pass filter. And there's a lot of documentation on the different types of blocks that you can utilize. And if you want to actually just search for blocks, you can hit this library browser, right? If you don't know what you're looking for, and it'll pop up a search and a lot of different interesting blocks that you can put together to do different things. So that's good for the Simulink part. We also will be using MATLAB to simulate a communication system, and I've provided an example script up here, right? So you can read all about the theory behind it, but pretty much if you're just looking to get this done as soon as possible, right? So the main thing that we're looking at is we're changing the sample size, we're changing where our random variables are centered, right? So we have a bit stream, right? So 0 is good, but instead of 4, we're going to change that to 1, right? And then sort of like this variable called 4 samples, it's going to be called 1 samples or something. I think we're also changing the variance. So when we change the variance, right, for each case, we're going to have to change both of these. So these variances refer to the variance for each of these random variables. So this plot already, or this script already plots the different things that you want. And then just looking at the confusion matrix, right? So these are going to be a way of representing weights. So, right, if we have like, so on this, we have our sample, and then here, right, so we have values that are centered about 1, and we have other values that are centered about 0, right? But sometimes if our variance gets too large, right, these 0 samples will start to float into or closer to this the wrong decision. And so another thing that we're changing is this decision boundary, right? So when we have samples centered about 0 and 1, a good decision boundary, right, is probably about 0.5. But as you can see, the variance gets too large. Some of our 0 samples will float into 1, and some of our 1 samples, right, some of our 1 samples are going to float into 0. So the idea behind a true positive, right, is we add up all of the samples that are 1 and are expected to be 1, right? So down here, we have a variable with our 1 samples that follow this normal distribution, right? So the regular bell curve and the distribution. So that's for the true positive. So suppose I wanted to find the true negatives or something, and there'll just be these 0 samples, right, that are below the decision boundary. Right, so these are classified correctly. They're truly negative in the sense that it's a 0. It's like a binary system. So that is for part 4 here. In part 5, we're going to be using the Arduino IR sensor and remote. So that's, you can find documentation on that in this user manual here. If you scroll down through table of contents, and I think it's this IR receiver module. Oops. Here. So you can find all the documentation on how to use this, how to get set up with it in this. And then we also want you to look at this frequency characteristic curve and determine what kind of filter that our IR sensor behaves like. So I think it's interesting to talk about filter theory, since a lot of these components that we're working with are actually filters in a large sense. So that's for that part. This last part, it's kind of more or less a review of last week, just making flowcharts, drawing a schematic of your project. So that should all be pretty straightforward. Yeah, I think that's sufficient for this discussion. I'll see you guys in the next video. Thanks.